You think words mean what they say. By the end of this, you will understand that for a model, words are coordinates, and that changes what understanding really is. Sit with that. An embedding is not a definition. It is not a memory. It is not a stored explanation. It is a position in space. When a model encounters a word, a sentence, or even an entire document, it does not keep the text as text. It converts it into numbers, not a few numbers. Hundreds, sometimes thousands, arranged as a vector. That vector is an embedding. Each number represents a dimension in a high-dimensional space. No human can visualize this space directly, but the model navigates it continuously. Every word you type becomes a point inside it. Meaning, for the model, is location. If two words are close together in that space, they are used in similar contexts. If they are far apart, they behave differently. The model does not know that a cat is an animal. It learns that the word cat appears in contexts statistically similar to dog, pet, or fur. Those similarities compress into coordinates. The geometry becomes the meaning. This is the first shift. You might assume that intelligence requires symbols attached to definitions, but embeddings operate without definitions. They rely on distribution, on patterns of co-occurrence, on how often and where things appear together. The sentence, "The lawyer filed the motion," becomes a vector. "The attorney submitted the request," becomes another. Those vectors will likely be close to each other, not because the model understands law, but because the statistical patterns of those words overlap across millions of documents. Closeness replaces comprehension. This space has structure. Clusters form. Topics gather into regions. Legal language occupies one area. Medical language occupies another. Informal speech drifts elsewhere. Embeddings allow the model to move through this landscape. When you ask a question, your words are embedded. The model searches for nearby regions, nearby patterns, nearby continuations. It predicts what usually follows from that location, not what is true, not what is intended, what is probable. This is why embeddings matter. They are the substrate of similarity. They allow retrieval systems to find relevant documents without exact keyword matches. They allow translation models to map sentences across languages. They allow recommendation systems to detect that two users who never met share behavioral proximity. Embeddings reduce complexity into geometry. Consider what this implies. If meaning is location, then ambiguity becomes overlap. A word like bank occupies multiple regions. Financial contexts pull it one way. River contexts pull it another. The embedding reflects this tension. The vector sits in a position influenced by both. Context shifts its coordinates slightly, enough to disambiguate statistically. But notice what never happens. There is no internal declaration that says, this word has two meanings. There is only a point in space influenced by usage patterns. The model resolves ambiguity not by reasoning about definitions, but by calculating which nearby continuation has the highest probability. The resolution feels intelligent. The mechanism is geometric. Embeddings also reveal a constraint. Because they are learned from data, their structure mirrors that data. Biases become spatial relationships. Associations that appear frequently compress distance. Rare connections stretch apart. If certain professions co-occur more often with one gender in training data, those proximities become encoded, not as opinions, as geometry. The model does not choose this, it inherits it. Now consider scale. Modern language models operate in spaces with hundreds or thousands of dimensions. Each dimension is not a concept you could name. There is no single animal axis or emotion axis. The dimensions are distributed representations, fragments of patterns, spread across coordinates. No single number carries meaning. Only the configuration does. This distributed structure gives embeddings power. It allows generalization. The model can encounter a phrase it has never seen before and still place it near similar phrases. Novel combinations become navigable because the space is continuous. Continuity enables prediction, but continuity also smooths distinctions. Sharp logical boundaries do not exist in this space. There are gradients, not categories. Nearness is relative. Edges blur. This is why models can appear fluent, yet struggle with precise counting or strict symbolic reasoning. Geometry handles similarity well. It handles discrete rules less cleanly. Embeddings optimize for pattern resemblance, not formal logic. There is another layer. When large systems perform retrieval-augmented generation, they embed both your query and millions of documents. They compute distances between vectors. The nearest neighbors are retrieved. Relevance becomes a matter of proximity. No document is understood. It is compared, ranked by geometric closeness, fed back into the model as additional context. The process feels like search guided by comprehension. It is search guided by distance metrics. Cosine similarity replaces semantic judgment. You might wonder whether this diminishes intelligence. It does not. It reframes it. Human cognition also compresses experience into associations. We group concepts. We sense similarity. We navigate mental space. But humans also attach intention, goals, and grounded experience to those associations. Embeddings lack that grounding. They do not arise from embodiment. They arise from text alone. The space reflects language about the world, not the world itself. This distinction matters. When a model produces an answer, it is sampling from regions of high statistical density. It is not consulting beliefs. It is not referencing lived experience. It is traversing a landscape shaped by billions of sentences. You are interacting with geometry trained on language, and yet the results can feel coherent, even insightful. That coherence emerges because human language itself contains compressed structure. Our texts encode norms, explanations, arguments, and narratives. When a model internalizes these patterns spatially, it acquires the ability to reproduce their surface logic. Embeddings are the compression mechanism that makes this possible. Without embeddings, every word would be an isolated symbol. There would be no measurable similarity, no gradient between concepts, no smooth interpolation from one idea to another. Embeddings create continuity where raw symbols offer none. This continuity enables translation across modalities as well. Images can be embedded into similar vector spaces. So can audio. When text and images share a compatible embedding space, alignment becomes possible. A caption can be matched to a photograph by comparing vectors. Different data types become comparable through shared geometry. The abstraction is radical. Everything becomes coordinates. If you remove the interface, the chat window, the generated paragraphs, what remains is a system adjusting numbers in a space too large to visualize, learning to position representations so that proximity mirrors statistical regularity. There is no inner voice, no hidden narrative, only vectors interacting through matrix multiplication. And yet from this, language emerges. Embeddings do not explain consciousness. They do not prove understanding. But they do explain how structured output can arise from pattern compression. They reveal that much of what we call meaning can be approximated through spatial relationships learned at scale. This should not be comforting or alarming. It should be clarifying. When you read a fluent paragraph generated by a model, you are observing the traversal of a learned landscape. Each next word chosen because its vector aligns with the current trajectory through space. The system is not asking, "What do I think?" It is calculating what lies nearest. If intelligence can be approximated through geometry, then perhaps some parts of our own cognition are less symbolic than we assume. That possibility remains open. The next time you see a model respond with precision, consider what made it possible, not insight, not intention, position.